All right, thank you everybody for being here. My name is Rassil Sayess. I'm a research support specialist at the Water Resources Institute. I'm going to be giving a little introduction on per and polyfluoroalkyl substances, or PFAS, before I introduce our speakers today and the FLX PFAS project. All right. Going back to 1938, which is when a chemist named Roy Plunkett was working for DuPont in Deepwater, New Jersey. He was trying to come up with an alternative to chlorofluorocarbon refrigerants that were poisoning people at their homes and food workers. So he was trying to come up with a better alternative for that, and accidentally came up with this chemical that was extremely inert and had very distinct properties of being very stable. And here on the left, you'll see that there is a reenactment of that discovery, and here's Roy Plunkett on the right. Fast forward a little bit to 1940s. Oh, and so what he discovered was what we know as Teflon, or PTFE. In the 1940s, that material was used in the Manhattan Project for the development of the atomic bomb. At the time, it was kept a secret, but then later in 1945 is when DuPont finally patented the chemical. In 1951, Roy Plunkett received the John Scott Medal from the city of Philadelphia for, and I quote, promoting the welfare, comfort, and happiness of humankind. And attendees of that event were given muffin tins that were lined with PTFE, so they were, greaseproof. And then from then forward, Teflon was used in more consumer industrial products. It wasn't until the 1960s and the 70s that there was a significant expansion of the use of PFAS in different industries. Hit forward. Come on. Move. All right. So the word PFAS is an acronym. It's short for per and polyfluoroalkyl substances. They are a group of man-made compounds. They're manufactured. You cannot find them naturally in the environment. And to this point, there are more than 6,000 PFAS that have been identified, depending on your preference for how you categorize PFAS, 2 carbons versus 1 carbon. But there are thousands and thousands of them. They are known to have this very characteristic carbon-fluorine bond that is the strongest bond in organic chemistry. It makes them extremely stable and resistant to most degradation processes. So you can imagine how something like that can be extremely useful in manufacturing products that could be beneficial for industrial and personal uses. They are known to have this cool-looking hydrophobic, it's not, the cursor isn't working, hydrophobic tail. And you can see a carbon chain that's either fully or partially saturated with fluorine here if you don't know much chemistry, which is fine. This is a C, this is a C, this is a C. Sometimes you find this fully saturated, and sometimes they're not fully saturated. But anyway, those bonds are what give the PFAS chemical a hydrophobic property. And then you have this oil repellent functional group or head. Here you have carboxylic acid. So it has both properties of being water repellent and oil repellent at the same time. And here, this one example I gave is of perfluorooctanoic acid, or PFOA, and this is one of just 2 of the compounds that are currently regulated by the EPA in drinking water. The thing about PFAS is that they bioaccumulate, or they build up in environments and in our bodies and aquatic ecosystems, and they persist. They're not easy to degrade, and that's what has earned them the label of forever chemicals. Some of the sources of PFAS that you see commonly, or we all probably use or don't know that we're using, but anything that is basically either nonstick, waterproof, oil-proof, probably have PFAS in them. So things like waterproof clothing and carpets and textiles that have been marketed as either, oil resistant or, waterproof. A big source of PFAS is firefighting foam or aqueous firefighting foam. It's called AFFF. That's actually the biggest source of PFAS and at least in the US. And we can talk a little bit more about that. But it's also used highly in the industry to make things like photolithography, anything that is used to make the chips that are in our phones or computers. They're used in paints and personal care products, hydraulic aviation fluids, you name it. So it's these materials these compounds are highly sought after in the industry, and I'll tell you a little bit about why we find them everywhere, basically. But they are everywhere. So here is a schematic of how PFAS gets introduced into the environment and how it cycles through. I'm just gonna take you briefly over some of the important parts of this diagram. First, you see here we have a manufacturing site. This can be a site that is either used to manufacture PFAS or is using PFAS to manufacture a different product. But in the process of that manufacturing, the company ends up discharging its wastewater. They're either directly into surface water or has some illegal disposal that happens off-site. It could also send the wastewater to be treated either on-site or onto a wastewater treatment plant. So there are multiple avenues that the waste from the production can end up in the water. But not only that, the manufacturing site itself has emissions that contain PFAS. They can transport PFAS from the site off to other areas, neighboring areas, or even further. But then when it rains, these chemicals end up being deposited onto the land. Another thing here that's interesting to look at is the landfill. So every time we finish with using a product that has PFAS, we toss it, it ends up in the landfill. This landfill ends up having either leaching into the environment or from the decomposing aspect over long periods of time. All that can end up in our water. But not only that, biosolids that sometimes get taken from landfills and applied to things like farm fields. While biosolids can be really beneficial for farm applications, if they contain PFAS, then that soil now has PFAS on it. So anything that grows in that soil has PFAS, or if we have animals that are grazing on farmland, the products from those animals and the animals themselves, they will probably have PFAS in their systems. Here's another big source of PFAS. You have airports. Now in airports, they use sometimes firefighting extinguishing just for practices. But airports, similar to firefighting training stations, also are big sources of PFAS. And the FLX PFAS team will go over that a little bit with you. But they also use hydraulic fluid, de-icing agents. All that stuff also contains PFAS. And here I wanted to just show we have public water systems that are used basically to treat source waters that end up in our tap. And if these systems are not, if they're not designed to take out PFAS from the water, then whatever goes in is still going to be entering our tap water. And these 50 to 80-year-old systems were not designed with removing emerging contaminants such as PFAS at the time. So this is really a big problem for community water systems. And so all of these sources, they end up polluting the water, or if there's a farmland that uses groundwater, all that ends up at the consumer level. And then when we end up also sending our water into wastewater treatment plants, then also if they're not equipped to remove PFAS on site, they also end up with having PFAS going cycling back into the environment. So this just gives a general idea of sources and how PFAS moves through the environment. So people are exposed to PFAS in a variety of ways, either through direct use or the indirect exposure to PFAS-containing products. You could be drinking water or consuming fish or shellfish that is contaminated with PFAS. Like I just mentioned before, if you're consuming meat or milk or eggs from livestock that have been raised on farms that have been contaminated with PFAS, that's also another way of exposure. But simple things also like eating pizza from, pizza-lined boxes or having grease-proof popcorn bags, all that is another way that you could be exposed to it. So we haven't said yet, like, what is the problem? Why is it a problem to be exposed to PFAS? And at this point, and for actually quite some decades now, there have been enough evidence to show that the exposure to PFAS to a high likelihood of certain things and low likelihood of others causes a variety of different problems in humans. Some of the really well-studied known ones is that it increases cholesterol levels. It impacts, it causes liver disease by changing liver enzymes. It has an increased risk of kidney and testicular cancers, as well as thyroid disease. And it has a whole suite of problems with newborn and unborn children. So as you can see, this is an issue that has been really becoming a public health issue, at least over the last decade or so, when more and more people became aware of this problem. So there was a lot of interest in locally from academia, but also from the public, as well as local watershed and advocacy groups, to knowing what is in our water, what is going on in our area, especially the Finger Lakes. So the PI of this project, Professor Damian Helbling, was conceptualizing this early in late 2022, and I still remember how he was super excited about him trying to take this project head on. And so the project had actually started totally unfunded in June of 2023 until it picked up funding from the Great Lakes Watershed Program in 2024. So I'm really excited to hear from Brune and Holly about the progress that the team has made over the last few years. And so with that, it's my pleasure to introduce Holly Archer and Brune Boukobza. Holly is from Florida. Go Gators, she will tell you. She's a senior in environmental engineering with a focus on sustainability and sustainable energy systems. She joined the FLX PFAS team about 2.5 years ago, and she's been involved ever since. She is interested in all things sustainability and will be going into the energy industry after graduation. Holly played softball for 10 years and likes reading, hiking, and the beach. And Brune is from Cleveland, Ohio, and is currently a senior at Cornell, but she's been finishing Bachelor's of Science and Master's of Engineering at the same time. Her academic focus is on sustainability and climate impacts, particularly on emerging contaminants and heavy metals. She's working on a really cool project right now, focusing on how artesian gold mining impacts mercury concentrations in Tanzania. And when she isn't researching, Brune loves to ice skate and play the piano. So please join me in welcoming Brune and Holly.
All right, hello everybody. Thank you for joining us today. So I am Brune and this is my teammate Holly. Today we will be presenting to you our Finger Lakes PFAS project. So essentially our project does targeted water sampling to identify these per and polyfluoroalkyl substances that Rassil explained to us in the Finger Lakes region. A special thank you to Dr. Damian Helbling and Rassil, of course, for helping us with this project. All right, so here's our agenda for today. We're going to start and talk about how this project was formulated. Rassil gave us a brief overview, but we're going to go a little bit more in depth here. And then we're going to talk about data collection, how exactly we get all of our samples, and then our results, really the interesting part, and then our community outreach, how exactly we get all of our information out into the public. All right, so starting with our project. So a little bit of background is that PFAS were regulated before 2023, except it was just at a state level. New York was one of those states. But then in 2023 spring, that's when the EPA set those national regulations. So 2023 is really when the whole nation became aware of the existence of PFAS. So as we can see here, the EPA regulations as of April 10th of 2024, there were 6 regulated, different regulated PFAS compounds. And overall, we want our maximum contaminant levels to be less than parts per trillion. Now, it is very important to remember that this is drinking water. Surface water is not, does not have these same regulations whatsoever. It's really, so once again, this is drinking water. So the levels we're going to show you, this is really just a reference point. Fortunately, we're not drinking the surface water, as you'll see later on. Now, as of our current administration, as of May 14th, 2025, so very recently, about 6 months ago, only 2 PFAS became regulated. So it went from 6 to 2, and that maximum contaminant level is 4 parts per trillion. And that is PFOA, perfluorooctanoic acid, as Rassil showed in our example, and then PFOS, which is sulfonic. All right, so when the project started in early of 2023, Damian was receiving a lot of emails from Ithaca residents being like, what is happening with all of our PFAS levels? Should I be concerned? What is this? And the thing is, why he was getting these emails was because when you would look up Cornell PFAS, his name was the first one to pop up. Except the issue is that he did not have any kind of substantial data to actually give to these folks. And that is where the project genesis was. So in the summer of 2023, Alex, our very first teammate who is now graduated, created this ArcGIS map that we are all looking at right now. So it is a map of New York State, and it has all of the sorry, not all, but some possible sources of PFAS. As Rassil had mentioned earlier, and how PFAS gets transported, these are really some of the main contenders. We have airports, power plants, landfills, and we're also interested in wastewater treatment plants as well. So if we zoom in, we can see that this was 1 year into all of our sampling. I came in the fall of 2023, and so did Holly as well, and we had one other teammate. And it was the 4 of us, including Alex, doing sampling. So we collected roughly 100 samples 1 year into the project. As you can see, it is mostly concentrated in the Ithaca area. And then just because that is where we are used to, and then this is the map without any of the layers of the airport, which we'll talk more about in depth a little bit later on.
Yeah, and a really important thing in our project has been this common thread of mentorship. Like Brune mentioned, we started with just 4 students in fall of 2023, and then we had 5 in spring of 2024. That's Brune and I on the bookends on that picture on the left. And then just last semester, we grew to 8. So that's 7 of us. I'm actually not in the picture on the right, but I promise I was still involved. But it's been really cool to see the organization kind of develop in this project. We kind of started, like Brune said, just sampling around, doing all the data analysis ourselves. But now that we have more people and we've been spreading more awareness, we've grown into different sub-teams. And so Brune and I are both sub-team leads. I'm the sub-team lead for data analysis and community outreach. And you're the sub-team lead for
the sample preparation and sampling.
Yeah, and so it's really nice to get the undergrads involved in this research and to also use that to spread awareness for this problem and just give young students an opportunity to gain skills and gain experience in this industry of emerging contaminants.
Yeah, and it's also really important to notice that we are a fully student-run project, and of course with the help of Rassil and Dr. Helbling. But other than that, it is fully almost undergrads, with the exception of some of us now master students, but started as all undergrads. But yes, fully student-run. Did you talk about 24 points?
Yeah. Oh yeah, I was actually, it was really beneficial because I was a TA for one of the important classes that you take as a sophomore in environmental engineering. And so I was able to use that experience to kind of get some of the students interested in the project. And it even was able to inform some of their final projects for the course. And so we were able to get new members from that kind of involvement there. And we've done stuff like that in the past, not just in that course, but with other courses and other professors. We've worked with them to also gain interest and spread awareness in our project as well as PFAS in general.
Yeah, just like today.
Yeah.
All right, so we're now going to move on to our data collection.
Yes.
How exactly do we get all of these samples?
Yeah, so these are some pictures of us sampling at a couple different locations, lakes, streams, ponds, and our samples are all grab samples, which are all taken at one point in time. And then each sample or group of samples, we kind of have changed this over the semesters, is accompanied by a field blank, which is a sample of deionized water that we fill up at the lab before we go. And then once we get to the sampling site, we open it and we pour it into an empty vial. And so we can catch any kind of contamination that may happen in that process. So we can take that into account with that group of samples that it's with when doing the data analysis.
Mm-hmm. And then, of course, since these are grab samples, meaning we go directly to the site, as you can see in the photos, and take it manually, it's very important to note that sometimes it can be very difficult to access these locations. Once I was going to the airport, and a lot of places are blocked off around the airport. There were some water bodies behind it that I was interested in, except when I was driving around there, I then saw gates and signs around the area that said, no trespassing, you will be prosecuted, no stopping or standing.
Yeah.
So
yeah, and then also it's important to note that since we are in the Finger Lakes, we have a very long winter, and a lot of the places that we plan our sampling around are boat launches and marinas. And from late October to like late March to April-ish, some of those places are just closed for the season.
Mm-hmm.
So like I was out in October last semester, and there were like half the places that I wanted to go to were just like closed for the season. So it's definitely a limitation that we've run into pretty frequently.
Yeah, but that also has allowed us to adapt over the past few years of this project, of learning what the good times are to go, and knowing when to do certain parts of the project throughout the years.
Yeah.
All right. So
so this is kind of initial sampling. I think this was after our first semester. The smiley faces are the points that we sampled. And as you can see, it's very highly informed by the map. As you can see, we have a few smiley faces around the airport over there and around the fire station. And then we have some near the wastewater treatment facility. So you can just see how even early on, like the map definitely influencing where we were going. And again, we were staying pretty local because only one of us had a car. And we also had a lot of interesting behavior happening around Ithaca that we wanted to see. This was kind of like first semester, kind of where we went around Ithaca.
All right, so now here are some fun photos of us taking samples. We have these two. So as you can see, in these photos, we try very hard to not go into the water.
As you can see in the middle.
Yes, in the middle, we have Holly holding one of our past teammates with a stick rope to make sure to not get the boots inside of the water. We have Alex on the right sitting on a tree stump. And then we have Laura in the middle, who's also a past team member, just bending down. And you can see that the water is pretty filthy sometimes, and we really sample from all sorts of different kinds of water bodies. You have a little creek in the middle, but then we have a pond on the left, and that's Cayuga Lake right there. All right, so once we've collected those samples, what exactly do we do with them? So they then get brought to the lab, and within a few weeks time range, they are prepared through a series of processes. Now, this is the specialty that myself is focused in on. So we start by taking a filter sample of a few milliliters of the sample. Our bottles hold 15 milliliters, so we have a little bit left over for our pH samples. Then we spike all of the samples with this internal standard to make sure they're all correctly calibrated on our right calibration curves that we create. And then finally, we pass it off to Rassil, who then measures them with our mass spectrometer. So this is our very fancy, we're very fortunate to have liquid chromatography and mass spectrometer. And this is what tells us all of the levels of PFAS that are inside of each water sample. So we started in this machine being able to identify 17 different PFAS, and it is now up to 24 PFAS since this past semester. So and then the two PFAS that are regulated by the EPA, the PFOS and the PFOA, are also included in those current 24 PFAS samples. How we initially chose those 17 samples, the 17 PFAS PFAS was because of those 6 that were initially regulated by the EPA back in April of 2024, and then different lengths of strands of PFAS. So typical one is 10 fluorine carbon bonds, but then we also have 9, 8, 7, and then more as well. And then finally, we prepare 8 standards for the calibration curve as well.
Now moving on to the important part, the results and data analysis, or maybe the exciting part.
Yes.
It's all important.
Very exciting.
I'm sure you guys remember this image that we showed earlier of a 1 year into sample collection that Brune showed earlier. And so now here is our map now, and we have collected over 340 samples. And we have been to 10 out of the 11 Finger Lakes. Not Canadice. I think Canadice is, you can't see it. I think it's right here.
Canadice is right in between Canandaigua and Hemlock.
Brune tried to go there, but she couldn't find a good access point. So we've been there, there's just no samples from there. But as you can see, it's still pretty highly concentrated in Ithaca, but we've also been to Syracuse because there's the airport up there. We've also been to Rochester, again, airport there too, but also interesting behavior at both of those locations.
Yeah, and so this layer on the map is solely our PFAS data. So I keep saying this layer, this map. I want to emphasize that at the end of this presentation, there will be a QR code that leads you to our website. And the map is fully interactive. So then you can toggle each layer, add, subtract, and we have many more than what we initially had between those airports and wastewater treatment plants. So this is just a snapshot of the interactive map. So like Holly said, currently, we over time really debated between what the best way to quantify each PFAS data as, because there are so many varying water body types. And we found the best way to show that was flowing freshwater. So this could be something like a stream, a creek, a brook, a river. Then we have standing freshwater, which is like a lake or a marsh, a pond, tap water, pretty self-explanatory. Temporary pooling, which could be like a pond or a puddle, for example. So it would be there only when it rains for a moment, temporary. And then, of course, wastewater treatment plant effluent, pretty self-explanatory as well. I do want to emphasize we do not take tap water samples any longer. We only did that at the very, very first few months of this project back in 2023, due to the fact that we wanted to really make sure our sample collection method was proper and we really had it down pat. So all of the tap water samples will be concentrated in the Cornell buildings as well. All right, and then this is overall our data of how many is collected from each. So pretty fascinating enough. We have the most in flowing freshwater. So remember again, like a river. However, we have found the highest amount of PFAS in our standing freshwater. And this does logically make the most sense because in flowing freshwater, PFAS can be transported for a long time. Except for standing, when you just have a pond, there's nowhere for it to exit. So logically it goes with our hypothesis as well, but quite interesting. All right, so remember when we showed you this map in the very beginning that Alex had made back in the summer of 2023? So we want to now zoom in to the map of Ithaca, just so that we can break it down a little bit easier, and that way when you interact with it at the end of this lecture, we can, it makes it a little bit easier to understand. So this map, as we can see, in Ithaca, this is Cornell, right around that area at the very right, that's Riley Robb. And then in the top right arrow, we have the Ithaca Airport, and then we have our main wastewater treatment plant on the left, which is where we've taken samples from. It's just to orient you well. And then now this is the map with our all of our data on it. So as you can see, we have quite a few high levels of PFAS in the airport area, and then also around the Cayuga Lake inlet. And then once again, you can see those tap water blue points are all located around Cornell.
So the size of the circle is.
Yes, so then that's the other thing that I'll talk about before I move on, is that the size of the circle depends on how the amount of total PFAS. So this is the 24 PFAS that we look for added together in those bubbles. So that's why if you look at the airport, there are very large bubbles. Those are very large concentrations. All right, so, and then just to highlight again, so you understand it well, that is a flowing freshwater that was taken around a river. Up top is standing freshwater. Those are the ponds we go to around the airport. Tap water, and then the wastewater treatment plant. All right, so now what happens when you click onto the bubble? So this is me simulating as if we were to click onto that bubble where the arrow is pointing on. So we have first the date and time, so you can see exactly when it was taken, of course, the sample name. Then you can see the source and type. This was the airport pond right when you enter in. If you've been to Ithaca Airport, you'll see that beautiful, most likely man-made pond. And then you also have our total measure of PFAS. So as you can see, this one was quite high of 247.29 parts per trillion. And then we also have other metadata. So we take the pH of all of our samples, last rainfall, longitude and latitude, of course. And of course, everything else is all the 24 PFAS that we identify.
Yeah, and so we also recently added a disadvantaged communities layer onto our map, which you can see in the yellow polygons all throughout the map. And then if we zoom into Ithaca, we can get a little bit of a better picture. So that yellow polygon right there is identified as an area with high environmental, health, and socioeconomic burdens. And so what we want to do in the future is identify any possible correlations between PFAS levels and this disadvantaged communities layer. So that's what we're hoping to do in the future, just to make sure, just to identify any trends and see what's happening there.
All right, so now we're going to go on to our first graph of every single PFAS of the 340 plus samples that we've taken. And they're all put onto the frequency and the levels of like their amounts of PFAS. So in the key of saying every PFAS listed, there's actually only 18 of the 24. And that is because the 6 that are not on there couldn't be quantified at all with the standards we have. Something to keep note. So overall, we are very happy with the results that we see. Majority of our samples are under the limit of detection and the limit of quantification. That's what LOD and LOQ mean. And then remember our drinking water standards set by the EPA were under 10 parts per trillion and 4 parts per trillion. And then it's quite interesting to look at the samples that are quite greater than 100 parts per trillion. Now, I do want to emphasize the fact that most of these samples that we've taken are not sources of drinking water. What does that mean? It means that the pond or the lake, essentially the water body that we sample from, is most not likely not going to be transported into our wastewater treatment plant. It's not going to be filtered into our drinking water at all. So don't worry, even though we do see a few of those samples being higher than 10 parts per trillion, up to 100 parts per trillion, we're not going to be ingesting that water anyway. However, it is important to know that we are not the only people on this planet. We also plenty of flora and fauna that do interact with these water bodies. I remember when I was sampling at this airport pond that did end up having almost over 1,000 parts per trillion. There were many geese inside of there with their little geese babies.
Geeslings?
Geeslings, yeah. So it would be, and I know there are plenty of other studies looking at how animals are affected by PFAS. So not quite our area, but it is still interesting to take note of.
Yeah, for sure. And getting into some more intricate data analysis, we put together this PFAS correlation heat map where you have the same PFAS on both the vertical axis and the horizontal axis. And the darker squares indicate a higher correlation of coexistence. So this means that in those darker regions that you can visualize on the map there, each square, if it's a dark color, that means there's a higher correlation that PFAS will also be found with the corresponding PFAS on the other axis, if that makes sense. So we did identify two key regions. So you have the top region, the top left region is the PFCAs. So that's the first homologous PFAS groups that kind of show up together. And then in more of the middle, that smaller square, you have the sulfonates, which also show up together. And so this is likely because that these groups are probably present in one product or source. And so we're trying to look into that further in our future research and to see kind of why this behavior is the way that it is. But it is probably due to that. And it's also important to note that we have at the bottom, you have these little squares. I don't know if you can see it. I want to point it out. I'm going to do it right here. These right here, the FTS groups, those are also present in both of the PFCA groups and the sulfonates. You can see this kind of block right here and this block right here that have a bit darker of a color than you would maybe expect. So that's also interesting behavior. And as you can see, there are these gray blocks kind of going through the middle. And so those are the PFAS that we struggle to quantify with our measurement, our mass spec. And so those we don't have a lot of data for that because we just have really been unable to quantify them.
But GenX, we can quantify. We just stopped after the new standards arrived. So the rest, yes, at these low levels is very hard to quantify.
Which is good because they're at low levels. So that's good.
And in case you don't understand this map whatsoever, the black, if you're thinking, oh, why is there a black diagonal line? Know that that is because it is matching up with the exact same PFAS. Yeah. So if you look at the very top left, that's PFBA. And then if you look at the very bottom left, that's PFBA. So logically, that's going to have a correlation of one because they're the same PFAS.
They're always going to be together.
Yes.
So I'm hoping that everybody is making sense of that graph. I know it's a lot to digest.
Yes.
But this one will be a lot easier. So recently, for the past, I think 6 months, since I think June over the summer, we've been visiting local locations. We go to 4 and we go every week to collect samples at around the same time every week. So we can kind of see the behavior over the weeks. And so we've been going to the Ithaca Airport Pond that we've been so heavily focusing on throughout this presentation. So we go to the airport pond, we go to Flat Rock, which is the source of Cornell's drinking water, I believe. And so that's why we go there, because that's important to see the behavior there. We go to the Ithaca Fire Training Station, which Rassil mentioned previously. The firefighting foam is a huge source of PFAS. And then we also go to the Cayuga Inlet because there is, it's the Ithaca Solid Waste Facilities adjacent to it. So we want to see if there's anything happening there. And so This is the behavior over those 6 months at the Ithaca Airport and the Fire Training Center. And we're only including these because at the other two locations, we never really found a whole lot of interesting behavior. So from this point forward, we are not going back to those locations. We're only going to continue going to the airport and the Fire Training Center. And these, again, are the only ones that had interesting data and data at all. So you can see here the blue Ithaca Airport. You can pretty much see it's kind of consistently high concentrations around 200 parts per trillion, like that sample that Brune highlighted previously. But what's more interesting is we have the orange Fire Training Center, which at the beginning you see these really high concentrations that kind of dwindle down. And we're interested to know if that is correlated with some kind of training event that they had at that June 11th time period. And then after that, it's kind of gone down. We're curious to correlate that with that scheduling. And we're also curious to see if there's that same behavior after that most recent graph all the way on the left, that tall one in November. We have data after that point, we just haven't run it through yet. So we are really interested to know what the behavior is looking like after that and if it matches what happens on the left half of the graph. So important things coming in the future. And we also have this correlation with airport proximity. We've taken samples around all kinds of airports. This is not just the Ithaca Airport, this is all airports in general. And it is the average total measured PFAS by proximity from nearest airports. You have miles on the x-axis, and then you have average total measured PFAS on the y. And you can see very clearly that it spikes pretty high, really close to the airport. And as you get away, like even as you get to like 2 to 4 miles away, it drops pretty significantly. It's important to note that that sample that Brune mentioned previously, that was like 1,000 parts per trillion or nanograms per liter. We did remove that because we deemed it as an outlier and we didn't want it to skew everything. And we also only include samples further than 200 meters apart, going off of that point of weekly sampling. And we didn't want going back to the same pond over and over and over again to skew our data in any way. So you can kind of take this in for a minute. And as you can see, like between 6 and 10 miles, it's pretty much like, no, like it's pretty much a normal sample at that point.
This is just Ithaca Airport?
This is all airports.
Yes.
So this is all of our data, and we have, I think Alex made this graph, and he just took all of the data points that we have within 10 miles from an airport, did a little coding thing on that, and yeah, so this is all airports, not just this here.
So includes Syracuse, Elmira, Rochester, Binghamton, and of course Ithaca.
Yeah.
All right, now we're going to our final point of the day, and this is our community outreach. So overall, including today, we have been to 9 different conferences and poster presentations. So our blue points are on Zoom and our red points are in person. Our very first conference that we have been to is Lake George, the New York State Federation of Lake Associations. So Lake George is up in right past Glen Falls. So on the right, the additional photo taken. So it's about a half an hour above Albany. Yes, that red dot over there. Very beautiful lake. That is me and Laura on the right side. You can see very beautiful outlook as well. And then, so this was really enlightening experience. Our first time, it was only barely a year into our into our project. And we got lots of great feedback and had some really good food too. All right, so then this is another highlight. This was in spring of 2025 at Cornell. It was KK Kwan Day. This was more tailored towards a renewable resource kind of project, but they still accepted our Finger Lakes project. And this was our first time doing a poster presentation as well. So very enlightening. There were also judges, so it was fun to have that kind of formality. On the right, you can see myself, and then our PI, Damian Helbling, he showed up, so sweet. And then on the left, we have myself and Bailey, who is now graduated as well. All right, then in a little bit later in the spring, this was in May, the post presentation was in March. So in May, then now three who have graduated, going from left to right. We have Laura, Alex, and Bailey. They went up to Syracuse. They had the interactive map on the iPad down there for people to play with, and a newly updated poster as well. And then along with this poster presentation, there was also a 5-minute lightning talk. So we've had lots of different experiences of lengthening our presentation, knowing how to speak to the right audience, knowing what to add, what to subtract, and then also staying within that time limit. So we have a lot of different kinds of rough drafts that we can pull from that we've made over these past few years.
And this was our most recent one just a few weeks ago at the Finger Lakes Research Conference. I actually went to this one this time and it was awesome. We did a poster and we also learned a lot about PFAS in fish. And so that was interesting. It was a great experience, great food there too. They had bacon wrap dates. It was awesome. But yeah, it was really nice. And we also, Brune has a fun anecdote for this one.
Yeah, we had somebody come up to us at this poster and tell us that they had been using our map to find places, find PFAS hotspots to take fish samples, fish collections. So
Yeah.
really, really heartwarming to hear that not only are we collecting all this data, but also helping inform these other researchers with their projects.
Mhm.
All right, so now we're going to finish up here. So we're going to start with feedback that we've gotten. Overall, very, very positive. We've had lots of people give us sampling locations. We always are looking for help on getting into certain locations because a lot of times they are private, like we told our anecdotes with the airport and the boat launches. So we have an email that we'll post at the end of this presentation. So if anybody happens to know specific wastewater treatment plant or a specific spot that is near one of the hot spots on the map that they would potentially be able to help us get into, we've already had previous and we're always looking for more.
Yeah, and then we've also gotten a lot of feedback on data analysis ideas. Even at the last conference I was at, I was talking to this gentleman and he was kind of proposing different ways. He asked me if we looked into rainfall, which we're in the process of doing that. So I was able to chat with him about that. And he also asked about looking into specific PFAS from sources, kind of like what I mentioned about those homologous groups and looking into that further. So we're getting a lot of ideas on where to go with our data analysis. There's so many directions that you could go. So definitely a lot of interest on that front. And we've also gotten feedback about clothing regulations. So the reason that we no longer go in the water is because we got feedback where someone was like, if your boots are in the water, they probably have PFAS on them. And so like that's also another feedback that we get. But in general, like Brune said, very positive. People are very interested in our results and our whole project in general.
Yeah, and so we will have a Q&A at the end of this presentation, but to answer a few frequently asked questions that we get at almost every single conference. First one being, where exactly are we going with this PFAS project? So overall, the project is to have a map of the prevalence of PFAS in the Finger Lakes. So this creates a relevant baseline that allows us to track the changes in the PFAS concentrations in this area that might come up with large changes to the landscape. For example, if there's a new source of PFAS that might be built, it's really helpful knowing the previous levels of prevalence of these contaminations. For example, one thing we're really on the lookout currently is that there is a plant up in Clay, which is near Syracuse, on Lake Oneida, that is going to be built. And we do know that these plants have previously had a large emitter of PFAS. So we do have data from this past year, so then we can compare it in the next few years. And then that ties into how our results tie into the EPA regulations. So as we mentioned before, and as can be concluded from before, federal and especially state regulations are constantly being reevaluated to reflect the availability of new information. So having this background on concentrations of surface water is one piece of the puzzle that might be needed to inform updated state and federal regulations.
Yeah, and we also sometimes get what are the potential sources at airports specifically? Because we always talk about how we frequent airports and we love the Ithaca Airport and we go there all the time. And so a lot of the times people are like, okay, why are airports so interesting? And fortunately for us, Rassil already answered that question in this setting. The de-icing, you have the aviation fluids, you can have the firefighting foam that you use in the airports, and all sorts of things like that. But people do ask us that because, again, we do talk about airports a lot. And then we also get asked, have we contacted people in charge of these large emitting PFAS sites that we've proven to be large PFAS emitting sites, or someone else has proven to be a large PFAS emitting site? And the answer is short and sweet. And it's just, first of all, it is hard getting into contact with them. And also that is just frankly not in the scope of our project. Ours is more to just inform the public, get data on the map, see what's happening, see how everything is behaving, and that's just not in the scope of our project. We're just supposed to be collecting data. So
yeah. All right, and to finish up today, here are our next steps of what's being planned. So as we showed earlier, we do have the disadvantaged communities layer. So this semester, we are planning on exploring the correlations between the communities and the PFAS, and potentially taking more samples around the layers that we have on the map. We're also converting the map into a dashboard. So as I stated earlier, we have a full website that has this map that's accessible. However, we would also like to put our graphs and other kind of information on that so that it really is available to the public and you don't have to come to our conferences to see that. And then also another nice metadata that would be interesting would evaluate the results of rainfall correlation, and then overall continue presenting our findings. I mean, we love coming to these conferences, hearing any kind of feedback, getting any kind of questions.
Yeah, and we're also working recently on formulating a scientific paper and hopefully submitting it to peer review by the end of the semester before Brune and I are gone, right? I guess you have another semester, but not within this project. But yeah, we're hoping to get that done this semester. And so that'll be really interesting to get that peer reviewed and put that together.
Very excited.
Yeah.
So a very big special thank you to the New York State Water Resource Institute and the Great Lakes Watershed Program for all of the funding that you have provided for us, and also for letting us present here today. And then on the left is all of our Helbling research group. So thank you to everyone who has helped out, provided feedback, and everything else. And then we will conclude with, here's the QR code you're more than welcome to scan. Also, if you just look up FLX PFAS Project or Cornell PFAS, the first link that pops up is our FLX PFAS Project. Yeah, and then there's our email, flxpfas@cornell.edu. All right, thank you so much for listening.
Thank you.